is B. Srinivasa. Today I would like to explain one more new topic on MPMC subject. So, the last presentations we have seen about 8086 hardware architecture, and today onwards we are going to see software architecture, why it is required, and all I am going to explain. So these are the topics: instruction format, addressing modes, and types of instructions I am going to explain. So we all know that this is the computer system, and basically the computer system is having two units. One is hardware unit and second one is software unit. And in this computer system, we are having mainly IO system, input and output system, and the CPU, central processing unit. And the central processing unit may have AL unit, control unit, and memory management unit. And this software, why we need this memory management? Memory management unit is basically two types: primary memory and secondary memory. And this primary memory again raw memory and RAM memory. And this RAM memory is a temporary memory, and this raw memory is a permanent memory. So this raw memory, suppose in our mobile phones, if you take this raw memory, is acting like a secondary memory here to store the instructions of the programming or the software and user data. But whether in the case of desktop computers or laptop computers, we are having this ROM for storage of DOS and BIOS instructions only, are called bootable instructions. And the secondary memory, user programs and user data can be stored, and operating systems can be stored by this secondary memory. Right. So here, what is the need of software that I am going to show you here. Right. So the CPU is the main hardware unit. So the CPU or central processing unit or microprocessor is going to operated by the three buses: control bus, address bus, and data bus. So here data can be stored in this memory, and data can be given and can be displayed by this IO devices. Right. So it is not an easy task. So these operations can be run through this in terms of software. So this is the 8086 microprocessor block diagram hardware. Right. So the 8086 can execute different types of operations using AL unit. So here I am giving one program how to subtract numbers in assembly language. So as I told in the previous class also, the program is having mainly 4 segments. But any program at least need 2 segments, one segment for data segment, another segment for the code segment. So this is the code segment where you write the program. So data segment to store data values and code segment to store programmer instructions. So this is one more program. So in this program, if you see this program here, we are not writing any brackets to any register or anywhere. But if you see here, this SI move BL comma SI is having bracket. What is bracket indicates? Bracket indicates here address location, because here we have written move SI comma 500. SI is allocated by 500, and this 500 becomes an address location of the memory by keeping these brackets. Right. So what is need of address? Because in the address locations of the memory only we can store the data. Right. So what is a software? You see, this, as we all know that the sequence of commands used to tell a microcomputer what to do is called as a program. Right, the sequence of commands. So if you see this program here, you see that the sequence here, step by step they are written: move x comma data, move ds comma x, move al comma data 1, move bl comma data 2, add al comma bl. Like that we will write the programs. Right, so the sequence of commands used to tell a microcomputer what to do is called as a program. Each command in a program is called an instruction. So each command, so what to do? Suppose move. means copy data from source destination. Add perform addition between two registers. Subtract. SUB means subtract the operation between two registers or the data to register like that. So each command in a program is called an instruction. So a program written in machine language, machine means here computer language, is referred to as a machine code or machine language, right? Because computer is a digital hardware device, so it can operate by using machine language or machine code. So the low level assembly language is designed for a specific family of processors that represents various instructions in symbolic code. So the difference between machine code and the assembly level language code is here in machine language code we will write zeros and ones programming, whereas in the assembly language we will write the program using symbolic code. Suppose moving of data. So we use MOV. Addition of data we use ADD. That is called symbolic code. Okay. So this is program. So what is a machine language? The machine language defines states that for computers to understand the commands provided in high-level languages like Java, C, C++, Python, the instructions have to be given in machine language or machine code that comprise of bits, binary bits. So the conversion of high-level language to low-level language or machine language is called by using interpretation or compilation, and by use the device called interpreter or compiler. So what is interpreter or compiler? It is a software programming to convert high-level language to low-level language. A compiler, also known as assembler, is needed for the proper execution of assembly language programs. Right. So assembly level language program to machine language, we need assembler. High level language to low level language or machine language is called as compiler. Okay. So what is assembly language here? See, the assembly language definition states that it acts as the intermediate language between machine level language and the high level language, because the programming languages are like this: machine level language first, and then high level assembly level language programming, then high level language programming. Today what we are using in the industry are called high level languages. So this exists between intermediate language and this is high level language and machine level language. Right? So it is in comparison to machine level language, assembly level language is easier to comprehend and use. So what's the difficulty of machine level language? Machine level language is not easy to use because we have to remember all the zeros and ones combinations. Suppose it is ASCII code, right? We have 256 combinations or 128 combinations at least. So we have to remember all the values in terms of zeros and ones. But in assembly level language and high level language, yeah, user interfacing words we use in the programming. Right. So assembly level language is basically a binary code. Basically binary code written in a form of that humans can read easily using instead of binary, we use uh, a 16-bit number, hexadecimal number system. So the assembler then takes the assembly code and translate it line by line to the corresponding bit or binary or machine level code. Right. So that being said, assemblers also have extra functionality like macros. So what is the assembly language in short? So assembly language is a easy language that humans can read easily instead of binary code. Right. So what is need of assembly level language? So every personal computer has microprocessor that manages the computer's arithmetic, logical, and control activities. This is the main functionality of the microprocessor, right? That performs arithmetic, logical, and control activities of the computer. So each family of processor has its own set of instructions. So this is the drawback. So every processor cannot use the same instructions. Every processor is having its own set of instructions. So when we change processor to processor, instruction set also will be changed. So this is the drawback of this assembly level language. For handling various operations such as getting input from keyboard, displaying information on screen, and performing various other jobs, these set of instructions are called machine level language. Right. So what is the drawback? The machine language is too obscure and complex for using in software development. We a number of applications or number of users is increasing, then we have to write more number of instructions, and this machine level language is becoming too obscure, means it's not easy to remember. So then what is the solution? They have gone for the a symbolic code, which is known as an assembly level language code. So these are the differences between machine level language and assembly level language. You can understand. So the differences in terms of, I have given level of programming, ease of comprehension, nature of the syntax, and the compilers, right? So and here dependency, areas of application, usage of mnemonics, generation of programming language, and risk of errors. You see the risk of errors, at least the risk of errors existing in the syntax of machine code is high, whereas in this assembly language risk of errors is very low, right? So various application means that we will see assembly language are used for real-time based applications mainly. Today we are also using in the 8051 or Atmel based microcontrollers for so many real-time embedded system applications. So what are the advantages of assembly code over machine code is it requires less memory and less execution time. It allows hardware specific complex jobs in an easier way. It is suitable for time critical jobs. It is most suitable for writing inter service routines and other memory resident programs. Okay, so these are some of the advantages of assembly language. It occupies very less memory compared to machine code. It allows hardware specific complex jobs. Okay, so this is one of the application of assembly language performs real-time operations. Right, whereas high-level language used to write those parts that are not time critical. Right. So this is the main why assembly line languages still they are using in the industries. High level languages are not suitable for designing of time critical job based applications. So what is real time? We all know that real time means the task specified by the application must be completed before any other input to the program that will alter its operation can occur. Right, if you define any job to be completed within specified time, so that the job must be completed before next operation is going to be incurred. That is what we call the real-time operation. Right, but these instructions are generally in have some formats. In 8086 also we are having 6 types of formats. Right, usually what is meant by instruction? Instruction is a job, right, or an action to be performed. So how it will perform? So these job or operations performed between CPU to memory or memory to IO or IO to memory or memory to CPU and CPU to IO. Like that, the data can be transferred from one location to another location or one device to another device. So in how many ways the instructions can be transferred? So they are no additional byte means 1 byte, 2 byte, 1 or 2 byte displacement, 1 or 2 byte immediate operands, 1 or 2 byte displacement followed by 1 or 2 byte immediate operand, or 2 byte displacement and a 2 byte segment address. Like that, we can transfer the data and we can form the instruction. Right. So here you can see that. So these are the instructions. Move ds comma ax means register to register. Move al comma data one. So here variable to register we are sharing. So like that, how the data can be transferred between register to register or operand to register or so memory to register, how it can transfer. Right. So instruction, how instruction can be executed basically. So instruction can be executed by using instruction fetch, instruction decode, operand fetch, execution, and operand store. So here these are the 5 steps to execute one instruction. Let's see here first one. So this is the main memory, and we are giving some instruction. Based on that instruction, the address goes to that main memory address location and fetch that instruction and giving it to the instruction register. That is what we call instruction fetch. Next one is called instruction decode. The instruction decode is having 2 steps. One is operand field and second one is called operation field that we will see in the next coming slides. So here operand fetch, third one is called operand fetch. So the operand fetch means here operand means data. So after fetching instructions, here we need to get the data. So the data is also stored in ROM memory or hard disk or somewhere. So that data will be goes through following through transmitted through RAM memory. That's called main memory and to the processor, that is the execution unit. So next one is execution. So here execution means operation field will be operated on data, and the last one is after performing that operated or operand data must be stored. So here this is one more way of instruction format. So one byte, two bytes with displacement, two bytes with display 16-bit displacement and 8-bit displacement, 2 byte with operand, 2 byte with 16-bit displacement with immediate operand. Uh, like that, here also they are giving different ways of instruction format that we will see. So here usually we are taking this of 6 types of instruction formats. 1 byte instruction, register to register, that is move, suppose if I write move AX comma BX, that is register to register. Right, register to or from memory with no displacement. If I write move AX comma bracket of SI is called memory to register, register to memory, right, with no displacement. If I write with displacement, if I write move AX comma bracket of SI plus 50, SI plus 5000, like that if you write, so that is what we call with displacement and with no displacement. Okay, so immediate operand to register. Suppose if I write move AX comma 5000, so the data 5000 is moved into the register. It's called immediate operand to register. Immediate operand to memory. So these are all will be explained in address modes, and that we will see later. So usually instruction is having two fields. Right. A machine language instruction format has one or more number of fields associated with it. One is called operation field and second one is called operand field. Operation field is also called opcode field and it is also called a mnemonic field. So this field, the CP executes instructions using the information which resides in these fields. Right. Suppose if I write move AX comma BX, move is called opcode and AX comma BX are called operands. So this is here you can see the opcode and operands. Opcode identifies the action to be taken. Operands identifies the data to be operand. Suppose you see move AX comma BX, add AX comma BX. So addition here between AX and BX. Here moving of data from BX to AX. So here it is called a movement or transferring or copying of data from BX to AX. Whereas here this ADD stands for addition of data between AX and BX registers. So usually we use this instruction format: label, opcode, operands, and comments. These are the four fields we use in the program: opcode, operand, and comments. Okay, see here for example, here the start is called label. Start is always followed by the semicolon or colon, colon here. And after the colon, you can find a move. Move is called opcode, and AX comma data. These are called operands. And here, what is happening will be explained by the comment line. Okay, this comment line. What is the comment here? So the memory data segment memory is allocated by the AX register here. So that you will see in the programming part. What is that? So what is displacement here? The data can be called from the memory locations are 16-bit memory locations. Why 8-bit and 16-bit? I told you already in the previous presentations, the memory organization. So data is available in terms of even bank or odd bank of memory. Right. So if you combine even bank and odd bank is called 16-bit. If you take separately, it is known as the 8-bit. So that's why we are having two types. Right. So 1 byte instruction, how it looks like. So this is the 1 byte instruction. So this is D0 to D7 means 8 bits here. So in these 8 bits, right? 6 bits for opcode. Here we are taking 7 bits, but 6 bits for opcode. Remaining two special bit indicators are maybe D bit, or maybe S bit, or maybe V bit along with W bit. Okay, so here in terms of W, sometimes they will take D, S, V, and Z bits. Right. What is D bit here or W bit? Right. W bit, some instances of 806 can operate in byte or a word operation. If W equal to 0, right, byte operations. If W equal to 1, word operations. Byte means 8-bit operations, word means 16-bit operations. So here D bit, the D bit in the opcode for instruction indicates the register to or register from. If D equal to 0, a source register. If D equal to 1, destination register. Means register is available in the destination. If D equal to 0, register is available in the source. Right. S bit. S bit means sign bit to perform signed operations. V bit means it indicates shifting or rotating of instructions. Z bit means it is used to string of operations to check the repeat instruction for Z0 flag if the result is 0 or not. Right. So if S bit and W bit both are 00, 8-bit operation, 01, 16-bit operation, and 11, 16-bit operation with extended 8-bit immediate operand. So these are the operations combination of S and W. So once again we will see what is W to indicate the byte operation or word operation. D means if the D equal 0, source register. Register is available at the source. If D equal to 1, then register is available at the destination. So see here how data can be moved to register to memory and register from memory to register with no displacement. Okay. So if displacement is 0, then the bits of these mode bits, mode D6 and D7 bits are 2 bits here, must be 0 0. If 0 1, only lower order displacement. If 1 0, both lower order and higher displacement are present. If 1 1, registered memory field treated as a register field only. Right? It's not treated as registered to memory. Right? So based on the bits available here, it may be with no displacement or with displacement. Right. See, next one here we are having next field 3 bits for register field. If this register field is 3 bits, so I can get 8 combinations 0 0 0 to 1 1 1. So then data can be moved from AX register. If it is 0 0 1, data can be moved from CX register. If 0 1 0 DX register, 0 1 1 BX register, 1 0 0 SP, and here they are taking when it is moving from AX to BX register, and here also they are taking segment register bits 0 0 0 1 1 0 1 1. These are available in the pin configuration of our 8086. Then these operations are performed based on the W equal to 1 and W equal to 0. Right? What is W equal to 0 means byte operation. That's why this AX is in the form of AH and AL, higher order and lower order. So here when W equal to 0, here you can see that AL, CL, TL, BL, AH, CH, TH and BH. Like that, a lower order or higher order it can take. Next one is R by M. This R by M is also 3 bits, D0, D1 and D2 bits. If R by M means register or memory, either register to memory or memory to register, will be taken as if it is 0 0 0, effective address A is equal to formed by BX plus SI plus displacement. If 0 0 1, effective address CX is equal to BX plus DI plus displacement. So like that, these registers all are used in the programming. So that's why here when you write the programming, these fields will be automatically set by the internal assembler. Right. So see here, I was already explained about all these things. For example, if I have the instruction move BL com AL. So now I want to copy data from AL to I want to copy data from AL to BL register. Then The opcode, the operation code already given for this move is 10010. Every instruction is having its own operation code. What is operation code? This move is called user humans understandable code, where computer understandable code is 10010. So even though if you write move, but the computer can read only it as 10010. Then how it can copy data from AL to BL? So it is D means direction. So AL is a source operand. So that's why D equal to 0. Right. W equal to B. W bit is 0. Why W bit is 0? Because AL, PL are byte operations. So 0. Next mode is 1 1. Register mode. Only these two are registers. No memory. So mode is in 1 1. Next registers I am taking AL, so it is 000. If you have doubt, you can see here. See here 00000 AL. Okay, and mode bit 1 1 register field. So like that, they are taking these instructions. And RYM is 001 register memory, 011 means AL register. So like that, when we write move BL com AL, computer internally generates the bit this code as right 88C3H. It's equivalent of the bit equivalent is equal to 88C3H. How? You see, for example, 1000 is 8, 1000 is 8. 1100 is 12 means C, 0011 is 3. Right. So this is equal to 88C3H. Like that, all the instructions can get modified into processor level or computer level from assembly level language. Right. So user can understand move BL comma AL, but computer cannot understand what is move BL comma AL. So next topic is addressing modes of 8086. So how to write the instructions so in is known as the addressing mode. So the addressing mode indicates a way of locating data or operands. In the programming is called as addressing mode. How to write the data or operands in the instruction is called as addressing mode. So an addressing mode describes the types of operands and the way they are accessed for executing an instruction is called addressing mode. And so first you should know the format of instruction, and we have seen that instruction format already. So addressing modes are based upon according to flow of instruction. Suppose the instructions are categorized into two types: sequence control flow and control transfer flow instructions. So before going to the instruction types, we have to know the addressing types. So first one is called immediate addressing mode. What is immediate addressing mode? So immediate data, right? So suppose here the data is 5. I should not write 5, it should be in terms of 16 bits. So we have to write 0005. Right, 00, even though these three zeros don't have any value, but we have to represent as 0005 H. H stands for hexadecimal. So each zero and each number is having 4-bit equivalent. So here AX stands for 16 bits. So that's why here 0005 is an immediate 16-bit data. Suppose it's 8-bit data, then we can write move AL comma 05H. So immediate data is a part of instruction. It appears in the form of successive byte or bytes. Right. So immediate data is a part of instruction. So I can perform the add AX comma 0005 also. Right. See here move CX comma 4929. Add AX comma 237. So here the operation between AX register and 2387H value. Right. So this is the immediate data addressing. Next, direct addressing. What it address here, the location of the memory is called address. This address location may be either 16-bit or 8-bit. So a 16-bit memory address offset is directly specified in the instruction as a part of it. Say for example here move x comma bracket of 0005. So the address 8086 massive programming, the bracket indicates address location. Without bracket, if read the instruction is called as data. direct addressing mode. So in the direct address mode, here I have one more address, move x comma 1235h. So the effect address will be calculated by nh into a ds plus 5000h. Right. So because I am thinking that the data is available in the data segment, so here I can write multiply with 10h because the address is completely 20-bit. So that's why you're multiplying with 10h, that becomes 20h, and this is the offset address. Next, the third one is register addressing mode. Means in the register addressing mode, the data is stored in a register and it is referred using the particular register. And if there is a data movement between register to register, if there is an operation between register to register, is called a register addressing mode. So here move and add are called operand, opcodes, and bx and ax are called as the operands. Right. Register indirect addressing mode. In this register addressing mode, right here instead of value, we are representing the address using register. So that's why it is called register indirect addressing mode. Move ax comma bx. So the source may be a indirectly specified register address. Next, indexed addressing mode. There are two index registers, SI and DI. So if you use this SI and DI in the brackets, then it becomes indexed addressing mode. So offset of the operand is stored in one of the index registers. Right, so that's why it's called as SI, because I told you data segment will use SI or PX or DI registers to store the offsets. Right, so register relative. This register relative is also having move AX comma bracket of SI. The data is available at an effective address found by either 8-bit or 16-bit of this SP, BIP, SI, DI like that address locations. Based index, so along with SI, if we use BX register also, sometimes the address location is not available or not possible to store in one register. Then we can take one more register, is called BX register, it's called based index. So that's why here address is formed of BX and SI. So that's why writing move AX comma bracket of BX and SI. Next one is relative based indexed with displacement. Right. So this is what we call the displacement. If my address is not available again, PX register and SI register address value, and also away from the 1, 2, 3, 4, 5 or somewhere 50, then we can write move AX comma 50H BX SI. So this is 2 power 8 is equal to 256, and this is less than 256 memory locations. So that's why it is called as 8-bit displacement. Right. And after that, we're having four important types of addressing modes, that they are intra-segment and inter-segment. Intra-segment and inter-segment, again two types. Intra-segment direct, intra-segment indirect mode, inter-segment direct mode and intra-segment direct mode. And these programs type of instruction we use in terms of jump and call instructions, that we will see later about this. But basically everywhere we will see only these 8 types of instructions addressing modes only. Right, once again we will see what are the addressing modes we are having. Right, there are 8 types of addressing mode: immediate addressing mode, direct addressing mode, register indirect addressing mode, register addressing mode, indexed addressing mode, register relative addressing mode, based addressing mode, relative based index addressing mode with displacement, and intra and inter-segment addressing modes. And these intra and inter-segment addressing modes can be within one segment if there is a jump from one location to another location, or if there is a jump from one segment to another segment. So these are the different types of instructions available in 8086. So the instruction set is data transfer instructions, arithmetic instructions, bit manipulation instructions, string instructions, program execution transfer instructions, processor control instructions, iteration control instructions, and interrupt based instructions. So by using these instructions only, we are going to write the program and we are going to operate the 8086 microprocessor. Right. So the data transfer instructions again four types: the data transfer of a word, input and output of port transfers are the instruction transfer the address and instruction transfer the flag data to flag register. So data transfer instructions, once again we are having instruction to how to transfer the word move, push, pop, push the data onto the stack, pop the data onto the stack from a register, exchange and translation. So these are some of the instructions and data transfer instructions for remaining port transfer, address transfer and flag transfer. Here we will see about all these instructions in the next presentation. So these are arithmetic instructions. Again, these are to perform addition, subtraction, multiplication and division. Right, what are the instructions we're having? Addition means ADD, add with carry means ADC, increment, decrement. Like that, we're having so many instructions to perform arithmetic operations of multiplication, both signed and for unsigned operations, and so on. Right. So these are the bit manipulation. Bit manipulation instructions are logical and shift and rotate operations. Here, these are important in so many operations. Right, and these are the bit manipulation of shift and rotation. Shift right, shift left, shift arithmetic, shift logical, rotate left, rotate right, rotate right with carry, rotate left with carry, like that. And string operations means how comparison of strings, transfer of data from one location to another location, finding of some characters in a string, finding of one words in a string or sentence, like that. We use these instructions, and these are the loop, branch and loop instructions. These are called as the call, return and jump instruction. These are the three instructions used for branch and loop instructions. So the branch and loop instructions are two types: conditional and unconditional. Right. So instruction to transfer the data using without any condition. So without any condition means it need not check the before by instruction whether they are equal or less than or greater than, like that. It can jump to the required location easily. But whereas using these instructions, that will test the condition. Suppose if I take JC, use it to jump if carry flag equal to 1. Right. This instruction helps us to jump to the required location if there is a carry. Right. If we take if J and C, jump to the location if there is no carry. Right. Jump if not equal. Jump if equal. Right. Jump if there is no signed bit. So all these condition flags are based on status of the flag register. And these are the processor controller: set carry flag, clear carry flag, right? Complement the carry flag, set direction flag, right? Reset the direction flag, set interrupt flag, clear interrupt flag. These are all also based upon the flag register only. How to set and reset the bits of the flag register. Right. Iteration or control instructions. How to repeat the process number of suppose I want to add 10 numbers. I want to compare 15 or 20 values. Then there is must be a loop instead of writing big program. So then we need this loop instructions. Loop if equal, loop if zero, and jump if CX is zero or not. So these are the interrupt instructions that we have seen in the previous interrupt presentation also. For a representation of interrupts, we are taking I and T, and to come back from the interrupt, we are taking I return, and for to check the overflow interrupt is called into O. Thank you. If you have any doubt, please feel free and ask me.